In the silence of the cosmos, our Earth spins gently in its orbital dance, carrying with it secrets of unimaginable ages. Close your eyes for a moment and let your consciousness drift backwards through time, past the familiar landmarks of human history, past the rise and fall of civilizations, past the age of mammals, past even the mighty dinosaurs that once ruled our world. We're journeying to a time before history itself had meaning, before the continents were no existed in their current forms, before even the great supercontinent Pangaea that once united all lands in a single, vast embrace. This is a voyage into what geologists call deep time, periods so immense that they challenge our very capacity to comprehend duration and change. 4.5 billion years ago, our planet was merely an incandescent sphere of molten rock, a cosmic forge spinning through space. The Earth of this primordial epoch bore no resemblance to the blue marble we know today. Instead, it was a hellish world of liquid fire, constantly bombarded by meteorites and comets in celestial bombardment that lasted hundreds of millions of years. The surface was a roiling ocean of magma, with temperatures exceeding 1,000 degrees Celsius. Time here wasn't measured in the familiar rhythms of days and seasons, but in eons, geological epochs so vast that our human minds can scarcely grasp their enormity. It's rather like attempting to count every grain of sand on every beach across all the world's coastlines, then multiplying that number by itself countless times. An exercise in contemplating infinitude itself. During this violent birth phase, something profound was occurring in Earth's upper atmosphere. Water vapor, released from countless cometary impacts and volcanic outgassing, began to accumulate in dense, choking clouds that shrouded the planet in perpetual twilight. The atmosphere was a toxic brew of methane, ammonia, hydrogen sulfide, and carbon dioxide, utterly hostile to any form of life as we understand it today. But gradually, imperceptibly, the cosmic bombardment began to wane. The planet's surface started to cool, and those vast atmospheric water reserves began their long condensation. The first rains in Earth's history began to fall, and what rains they were. Picture precipitation that continued not for days or weeks, but for millions upon millions of years. These primordial deluges gradually filled the lowest basins on Earth's cooling surface, creating the first oceans whilst vapors slowly condensed from an atmosphere still deadly to any life we might recognize. These ancient waters were unlike any seas that would follow. They were hot, nearly at boiling point in many places, and filled with dissolved minerals leached from the cooling rocks. Iron gave them a rusty red hue, while sulfur compounds painted them in shades of yellow and green. The earliest oceans were more like vast chemical laboratories than the clear blue waters we might imagine. And yet, within these seemingly hostile conditions, something magical was beginning to stir. In the depths of these primordial waters, processes both subtle and monumentally powerful began to shape Earth's destiny. The story of our planet's geological personality was about to begin, written in stone and time across billions of years. Deep beneath those first turbulent seas, the Earth's interior remained a dynamic, churning realm of molten rock. Like bubbles rising slowly through thick golden honey, pockets of less dense material began their patient ascent through the magma. This was the birth of our planet's first continental crust, not the familiar landscapes we know today, but something far more primitive and alien. These earliest land masses were nothing like the stable continents of our current world. Instead, they emerged as small volcanic islands scattered across the global ocean like cosmic petals floating upon an endless blue expanse. Each island was a temporary creation, born from underwater volcanic eruptions and constantly reshaped by the relentless forces of erosion and further volcanism. The rock that formed these primordial lands was predominantly granite, the same mineral foundation that today supports our greatest mountain ranges. But this granite was being born grain by grain, crystal by crystal, in a process so gradual that millions of years would pass before even small changes became apparent. Each crystal formation was a tiny act of geological creation, adding to the slowly growing foundations of future continents. Imagine standing on one of these ancient volcanic islands, surrounded by an ocean that stretched unbroken to every horizon. The atmosphere would have been thick and heavy, filled with volcanic gases that created spectacular sunsets of orange and purple. The only sounds would have been the constant rhythm of waves against volcanic rocks and the occasional rumble of distant eruptions. There were no living voices yet, no rustle of leaves, no cry of birds, no buzz of insects. Only the profound geological silence of a world still learning to exist. The winds that swept across these primordial lands carried nothing but the mineral scent of cooling lava and the salt spray of ancient seas. These were the Earth's first beaches, carved from black volcanic glass and pumice, constantly reshaped by waves that had traveled across thousands of kilometers of open ocean without encountering any other obstacle. As millions of years passed, something remarkable began to occur. These scattered island continents started to exhibit a subtle but persistent tendency to drift towards one another. Invisible forces deep within the Earth's mantle were beginning to assert themselves. The first stirrings of plate tectonics, the great engine that would drive continental drift for all of Earth's future history. Picture the Earth during this epoch as a living organism learning to breathe, its crust expanding and contracting in slow, regular rhythm spanning millions of years. Deep beneath the surface, vast currents of molten rock began establishing circulation patterns that would endure for billions of years to come. These convection currents move with all the patience of geological time, carrying heat from the Earth's core towards the surface in a process as inexorable as the tides. The Earth's first tectonic plates began to move like leaves floating on the surface of a slowly circulating stream. Their movement was almost unimaginably slow, roughly the same speed at which human fingernails grow, yet this seemingly imperceptible motion was laying the groundwork for all future geological drama. Some of these early plates drifted toward each other with the inevitability of destiny, whilst others were carried apart by the deep currents beneath. Where plates converged, the first primitive mountain ranges began to rise. These weren't the towering peaks we might imagine, but rather gentle swells in the Earth's crust, pushed upward by the immense but gradual pressure of colliding landmasses. Where plates separated, fresh magma welled up from below, creating new oceanic crusts and gradually widening the gaps between continental fragments. It was during this period that Earth developed its first true geological character. The continents were no longer merely random accidents of volcanic activity, but active participants in an elegant planetary choreography. Each movement, however imperceptible, carried within it the seeds of future geological epochs. Every shifting plate, every rising mountain, every opening ocean basin was writing the first chapters of Earth's autobiography in stone. In the zones where these early tectonic plates met and ground against each other, something extraordinary began to happen. The immense pressures and temperatures generated by these collisions created the planet's first supermountains, peaks that dwarfed anything in our modern world. These ancient giants rose like colossal stone fingers reaching towards the heavens, some reaching heights that would make our current Himalayas seem modest by comparison. 3.5 billion years ago, when Earth was still young and learning the rhythms of geological time, these supermountains dominated the landscape like stone cathedrals dedicated to the worship of deep time itself. Their peaks were shrouded in the thick, alien atmosphere of the early Earth, whilst their roots extended deep into the continental crust, anchoring them against the slow but relentless forces of erosion. The climate around these ancient peaks was unlike anything we might experience today. The atmosphere was still rich in carbon dioxide and other greenhouse gases, creating a warming effect that kept surface temperatures far higher than they would be in later epochs. But the sheer size and elevation of these supermountains created their own weather patterns, forcing the primitive atmosphere to rise and cool as it encountered their massive bulk. Picture rains unlike any in Earth's current climate, precipitation that could continue for not just seasons or years, but for entire centuries without pause. These prolonged deluges slowly but persistently carved into the granite faces of the supermountains, creating the first river valleys and beginning the long process of erosion that would eventually bring even these giants low. Each raindrop that fell upon these ancient peaks was performing the work of countless sculptors, gradually wearing away the rock grain by grain. The water didn't simply run off and disappear, but rather collected the dissolved minerals from the weathering granite and carried them down into surrounding seas. This process was creating Earth's first mineral-rich soups, oceanic solutions that would prove essential for the greatest transformation yet to come. The sound of these ancient rains echoed through valleys that had never known any other voice. For millions of years, this percussion of water against stone was Earth's only music, a geological symphony that played out across vast timescales. The resulting rivers were the planet's first highways, carrying not just water but the chemical building blocks that would soon make possible the most profound revolution in Earth's history. At the bases of these supermountains, in sheltered pools and quiet backwaters protected from the constant rain, something unprecedented was beginning to stir. Complex molecules, chains of carbon, oxygen, hydrogen, and nitrogen atoms, were starting to organize themselves into increasingly sophisticated arrangements. These weren't yet alive in any sense we would recognize, but they represented the first tentative steps towards something that would eventually transform not just Earth's surface, but its very atmosphere and climate. In warm pools sheltered by the shadows of ancestral supermountains, protected from the harsh radiation of a young sun and the constant churning of the open seas, a magnificent transformation was slowly unfolding. The random molecular dance that had been occurring for millions of years was beginning to show signs of order and purpose. Chains of carbon atoms, the fundamental building blocks of all life as we know it, began linking with oxygen, hydrogen, and nitrogen in patterns of increasing complexity and stability. Think of this process as resembling musicians in a vast orchestra, initially playing random notes but gradually beginning to discover harmonies and rhythms. These early molecular arrangements weren't yet alive, but they possessed something that purely inorganic matter had never shown before, the ability to influence their own continued existence. Some of these molecular chains developed the remarkable property of catalyzing the formation of similar chains nearby. Others began to form protective boundaries around themselves, creating the first primitive membranes. Still others developed the ability to store and transfer information about their own structure, the earliest ancestors of DNA and RNA, the information storage systems that would eventually govern all biological life. The process was extraordinarily slow and patient, even by geological standards. For every successful molecular arrangement that managed to persist and reproduce, millions of others dissolved back into the warm waters without leaving any trace. Yet gradually, inexorably, these chemical experiments were becoming more sophisticated and more stable. The pools where this molecular evolution was occurring were like laboratories scattered across the early Earth's landscape. Some were warm springs heated by geothermal activity. Others were shallow lagoons warmed by the intense radiation of a young sun. Each provided slightly different conditions, different mineral concentrations, different temperatures, different levels of protection from destructive forces. After perhaps 100 million years of this chemical experimentation, something extraordinary occurred. Some of these molecular arrangements crossed the invisible line between complex chemistry and simple life. They developed the ability not just to persist, but to actively reproduce themselves, to create copies that carried forward their essential characteristics while occasionally introducing small variations that might prove beneficial. These weren't cells as we would recognize them today, but rather the first proto-life chemical systems that could grow, reproduce, and evolve. They had no consciousness, no purpose beyond their own continuation, yet they represented a revolution as profound as any in cosmic history. For the first time in the universe's entire existence, matter had learned to organize itself in ways that could persist, adapt, and dream of greater complexity. 3.8 billion years ago, emerging from the chemical soups of Earth's primordial pools, the first true living organisms finally appeared. These pioneering life forms, known to science as archaea, were so fundamentally different from any life in our current world that encountering them today would be like meeting genuine aliens on their own home planet. These ancient archaea were the ultimate extremophiles, thriving in conditions that would instantly destroy any modern organism. They breathed not oxygen, but methane and hydrogen sulfide. They fed not on organic matter, but on raw sulfur and metal compounds. They flourish in boiling acid springs, in crushing oceanic depths, and in environments so toxic that they would dissolve modern equipment within moments. Picture these microscopic pioneers as the universe's first true adventurers, boldly colonizing every extreme environment that early Earth had to offer. Volcanic thermal springs that bubbled with temperatures exceeding boiling point became their preferred neighborhoods. Acidic pools with pH levels that would instantly burn through human skin were their comfortable homes. Deep ocean trenches where the pressure would crush submarines became their hunting grounds. Each individual Archean cell was a masterpiece of biochemical engineering, a microscopic universe of activity that processed energy and materials with an efficiency that still amazes scientists today. Their cell walls were constructed from materials unknown in any other form of life, allowing them to maintain their integrity in environments that would quickly destroy conventional biological membranes. These remarkable organisms established the first truly global ecosystem, spreading to every available niche on the early Earth. They colonize hot springs in what would eventually become Yellowstone. They thrive in the crushing depths of oceanic trenches. They found ways to survive and multiply in desert salt flats and frozen tundra. Wherever liquid water existed, no matter how extreme the accompanying conditions, Archaea found a way to call it home. But perhaps their most important achievement was the development of increasingly sophisticated methods for extracting energy from their environment. Some learned to process hydrogen gas, others mastered the art of metabolizing sulfur compounds, and still others developed the ability to derive energy from simple chemical reactions that occurred naturally in their surroundings. And then, slowly but inevitably, some of these remarkable Archaea began developing what would prove to be the most revolutionary capability in the history of life on Earth, the ability to harness the inexhaustible power of sunlight itself. The development of photosynthesis was not a sudden breakthrough, but rather the culmination of millions of years of gradual biochemical innovation. Imagine the first primitive organisms that could supplement their chemical diet with solar energy. They possess an almost magical advantage over their neighbors who remain dependent on the limited chemical resources of their immediate environment. These early photosynthetic organisms, the first cyanobacteria, also known as blue-green algae, began what can only be described as a silent revolution. Like cosmic artists working with brushes made of sunlight, they slowly began to change the very color of Earth's oceans. The rusty, iron-rich waters that had dominated the planet for billions of years gradually began taking on new hues as these microscopic painters multiplied and spread. The oceans of 3.5 billion years ago were a palette of colors almost unimaginable today. Iron dissolved in the seawater created tones ranging from deep burgundy to bright orange, whilst various sulfur compounds added yellows and greens. The sky above was often orange or pink, colored by methane and other gases that would be toxic to modern life. Into this alien seascape, the cyanobacteria introduced entirely new colors. Their photosynthetic pigments began painting streaks and patches of blue-green across the ancient waters. Over millions of years, these living artists created the first underwater forests, not made of trees or kelp, but of countless trillions of microscopic organisms working together to capture sunlight and convert it into biological energy. The process was gradual beyond human comprehension. Individual cyanobacteria were invisible to any hypothetical observer, yet their collective impact slowly transformed entire ocean basins. They built curious structures called stromatolites, layered towers of rock and living material that grew like underwater cathedrals. These ancient reefs, some of which survive as fossils today, were among the first large-scale constructions created by living organisms. Season after season, year after year, millennium after millennium, these microscopic organisms continued their patient work. They multiplied in the warm, shallow seas, forming vast mats that stretched for kilometers along ancient coastlines. They created the first biological communities, where different species of bacteria worked together in cooperative relationships that increased everyone's chance of survival. But as these cyanobacteria spread and multiplied, they were also producing something unprecedented in Earth's atmosphere, a waste product that would eventually prove to be both catastrophically destructive and ultimately essential for all complex life. That waste product was free oxygen. The Great Oxygenation Event, beginning approximately 2.4 billion years ago, represent perhaps the most dramatic environmental transformation in Earth's entire history. It was our planet's first major climate crisis, yet unlike later extinction events, this one was caused not by asteroids or volcanoes, but by the success of life itself. For billions of years, Earth's atmosphere had contained virtually no free oxygen. The existing life forms had evolved in this anaerobic environment and were not just adapted to it, they were completely dependent on it. Oxygen, for these ancient organisms, was not the life-giving gas we know today, but a highly reactive poison that could destroy their cellular machinery within moments of exposure. As cyanobacteria continued to multiply and spread across the world's oceans, they steadily pumped more and more oxygen into the atmosphere as a waste product of their photosynthesis. At first, this oxygen was quickly absorbed by iron and other metals dissolved in the seawater, preventing it from accumulating to dangerous levels. But eventually, the rate of oxygen production exceeded the environment's capacity to absorb it. Picture this transformation as the ultimate slow-motion environmental catastrophe. Unlike the sudden impact of a meteorite or the rapid eruption of a supervolcano, the oxygen crisis unfolded over millions of years. Generation after generation of anaerobic organisms found their world slowly becoming more toxic, their safe havens gradually shrinking, their very existence increasingly precarious. The crisis reached its peak when free oxygen began accumulating not just in the oceans, but in the atmosphere itself. For the first time in Earth's history, this reactive gas began to make up a significant percentage of the air. The sky itself was becoming poisonous to most of the life forms that had dominated the planet for over 1 billion years. Entire oceanic ecosystems collapsed as oxygen levels rose beyond the tolerance of anaerobic life. Vast populations of archaea and primitive bacteria succumbed to oxygen poisoning, creating the first great extinction in Earth's history. In many ways, this was far more devastating than later mass extinctions because it affected virtually all life on the planet simultaneously. Yet, as is so often the case in Earth's history, this apparent catastrophe carried within it the seeds of unprecedented opportunity. Crisis and innovation have always been partners in evolution's dance, and the oxygen crisis was no exception. Some organisms didn't merely survive the new oxygen-rich environment. They learned to exploit it. These evolutionary innovators discovered something remarkable. Oxygen, despite its toxicity to anaerobic life, could be used as a tremendously powerful source of energy. Aerobic respiration, the process of using oxygen to burn organic molecules for energy, proved to be far more efficient than any of the energy generation methods that had evolved previously. Think of this discovery as comparable to the moment early humans first learned to control fire. Just as fire can be devastatingly destructive yet immensely useful when properly harnessed, oxygen represented both danger and unprecedented opportunity. The organisms that successfully made the transition from anaerobic to aerobic metabolism gained access to energy resources that made their ancestors seem primitive by comparison. This abundance of available energy opened doors that had never existed before. For the first time in Earth's history, organisms could afford to invest energy in complexity rather than mere survival. Cells could grow larger, develop more sophisticated internal structures, and begin the evolutionary experiments that would eventually lead to all multicellular life. The stage was now set for one of the most important partnerships in the history of life on Earth, a collaboration so successful that it still powers every cell in the human body today. In a moment of evolutionary inspiration that continues to amaze scientists, certain large cells made a decision that would change the course of life forever. Instead of simply consuming smaller organisms as food, some began inviting them to take up permanent residence as internal partners. This biological merger created the first eukaryotic cells, organisms with nuclei and complex internal structures. Picture a large, primitive cell encountering a smaller one that had mastered the art of aerobic respiration. Instead of digesting the smaller cell, the larger one offered protection and resources in exchange for a steady supply of energy. The smaller cell became what we now call a mitochondrion, the powerhouse that still energizes every plant and animal cell on Earth today. This wasn't merely a temporary arrangement, but a permanent merger that created something entirely new. The two cells became so interdependent that they could no longer survive separately. The large cell provided protection and raw materials, whilst the smaller cell served as a living power plant, using oxygen to generate far more energy than either could produce alone. The success of this partnership was extraordinary. Eukaryotic cells could afford to be larger and more complex than any previous life form because they had access to the abundant energy provided by their internal power plants. They could invest resources in developing specialized internal structures, organelles that perform specific functions within the cell. Some eukaryotes acquired chloroplasts through a similar partnership, gaining the ability to perform photosynthesis. Others developed elaborate internal membranes, complex genetic systems, and sophisticated methods of reproduction. The possibilities seemed endless when energy was no longer the limiting factor in cellular development. For hundreds of millions of years, these single-celled eukaryotes experimented with an almost infinite variety of forms and lifestyles. They evolved into an amazing diversity of microscopic organisms, some that looked like tiny flowers, others that resembled miniature jewels, still others that moved through the water like microscopic dancers. These advanced single-celled organisms created the first truly complex ecosystems, where different species specialized in different roles and depended on each other for survival. Predator-prey relationships evolved, along with symbiotic partnerships and competitive strategies. The microbial world became a testing ground for nearly every major biological innovation that would later appear in larger, multicellular organisms. But perhaps the most revolutionary experiment was yet to come. After mastering the art of single-cell complexity, some of these organisms began exploring an entirely new possibility, the concept of cooperation on an unprecedented scale. In the tranquil depths of ancient oceans, approximately 1.2 billion years ago, a transformation began that would ultimately lead to all the complex life we see around us today. Groups of eukaryotic cells began experimenting with something that had never been attempted before in Earth's long history: permanent cooperation between individual cells to create larger, more capable organisms. The first attempt at multicellularity were tentative and experimental. Small clusters of identical cells began sticking together, forming colonies that were stronger and more resilient than any individual cell could be. But gradually, some of these colonies began to develop something unprecedented: cellular specialization. Imagine the first multicellular organisms as tiny communities where different cells took on different roles, much like the specialization we see in human societies. Some cells became dedicated to gathering sunlight for photosynthesis. Others specialize in processing nutrients. Still others focus on providing structural support or protection from predators. These early multicellular pioneers resembled underwater gardens in miniature. They grew in delicate, branching patterns that swayed gently with the ocean currents. Some formed thin sheets that carpeted the seafloor. Others grew upright like microscopic trees. And still others developed complex three-dimensional structures that maximize their ability to capture nutrient from the surrounding water. The oceans of this period were vast, peaceful aquariums filled with these experimental life forms. There were no large predators to threaten them, no fierce competition for resources. This was a time of pure biological exploration, when life was free to try countless different approaches to multicellular living without the pressure of survival that would characterize later periods. The diversity that evolved during this era was extraordinary. Some multicellular organisms developed the ability to move through the water using coordinated beating of tiny hairs called cilia. Others remained anchored in place but developed sophisticated methods for capturing food particles from the surrounding water. Still others learned to break down and digest complex organic molecules, becoming the first true decomposers. Sexual reproduction evolved during this period, allowing organisms to combine genetic material from two parents and create offspring with new combinations of traits. This innovation dramatically accelerated the pace of evolution, as beneficial mutations could now be combined and spread through populations much more quickly than before. The first complex life cycles appeared, with organisms alternating between different forms during their lifespans. Some would spend part of their lives as single cells and part as multicellular colonies. Others developed distinct juvenile and adult forms, each adapted for different environmental conditions or life strategies. Throughout this entire period of biological innovation, the continents themselves were continuing their own slow but dramatic transformation. The small volcanic islands and fragments of earlier eras were gradually being assembled into larger landmasses through the inexorable forces of plate tectonics. Deep currents in Earth's mantle continue their ancient circulation, carrying pieces of continental crust across the planet's surface like passengers on an incredibly slow conveyor belt. Some of the crustal fragments collided and merged, creating larger landmasses. Others were stretched and torn apart, opening new ocean basins between them. The dance of plate tectonics was entering a new phase, one that would culminate in the formation of Earth's first true supercontinent, a massive landmass that would unite most of the planet's dry land into a single, enormous continent for hundreds of millions of years. 1.1 billion years ago, like pieces of a cosmic jigsaw puzzle finally finding their proper places, the scattered continents and island chains of Earth began converging toward a common destination. The forces that had been quietly rearranging the planet's surface for billions of years were about to achieve something unprecedented: the creation of Earth's first supercontinent. This ancient landmass, which geologists call Rodinia, was unlike anything that had existed before in Earth's history. The name Rodinia comes from the Russian word meaning homeland, and indeed, this vast continent would serve as home to most of Earth's dry land for hundreds of millions of years. Picture a single landmass so enormous that it stretched from the North Pole to the South Pole, encompassing nearly all of the planet's continental crust. Rodinia was surrounded by Morovia, a global ocean even more vast than the Pacific is today. This was a world of extremes, one gigantic continent and one enormous sea, with no other major landmasses to break up the monotony. The formation of Rodinia was not a sudden event, but rather the culmination of millions of years of gradual continental convergence. As the scattered pieces of earlier continents drifted toward each other, they collided in slow-motion crashes that lasted millions of years and raised mountain ranges taller than any that exist today. The Grenville Mountains, the remnants of which can still be found in eastern North America, were formed during Rodinia's assembly. These ancient peaks once rivaled the Himalayas in height and grandeur, standing as monuments to the incredible forces involved in continental collision. The climate of unified Rodinia was remarkably stable and uniform. Without oceanic barriers to disrupt atmospheric circulation, weather patterns were able to develop on a truly continental scale. Vast high-pressure systems could persist for centuries, whilst equally enormous low-pressure zones brought consistent rainfall to regions thousands of kilometers across. The interior of Rodinia was largely desert, as it was simply too far from the ocean for moisture-bearing winds to penetrate effectively. But the coastal regions enjoyed mild, subtropical climates that supported the most advanced life forms Earth had yet seen. Rivers meandered for thousands of kilometers across Rodinia's surface, creating the first truly continental-scale drainage systems. These rivers were lifelines to the early ecosystems that were beginning to colonize the margins of the supercontinent. Along their banks, complex communities of microorganisms created colorful mats that may have been visible even from space. These bacterial communities were Earth's first experiments in large-scale terrestrial life. The shores of Rodinia were unlike anything we see today. Vast tidal flats stretched for hundreds of kilometers, exposed to the air during low tide and submerged beneath warm, mineral-rich waters when the tide returned. These intertidal zones became laboratory for evolution, where life forms experimented with surviving both underwater and in open air. It was along these ancient shores that some of the most important innovations in Earth's biological history began to appear. Organisms started developing more complex body plans, with distinct tissues and organ systems that allowed them to grow larger and more sophisticated than any previous life forms. The Ediacaran organisms, named after the Ediacara Hills in Australia where they were first discovered, represent one of the most remarkable chapters in life's early history. These were Earth's first large, complex, multicellular organisms, and they appeared around 600 million years ago in the shallow seas surrounding Rodinia. Picture creatures unlike anything in today's world, organisms that seem to belong more to an alien planet than to Earth. Dickinsonia, one of the most famous Ediacaran fossils, resembled a quilted mattress up to a meter in diameter. It had no mouth, no digestive system that we can identify, and no obvious means of locomotion, yet somehow it thrived in the ancient seas. Sprigina looked rather like a primitive arthropod with a crescent-shaped head and a segmented body, but it lacked any of the hard parts, shells, claws, or teeth that would characterize later animals. Tribrachidium was a three-armed disc that sat on the seafloor like a living decorative medallion, filtering nutrients from the water through mechanisms that remain mysterious to this day. These Ediacaran organisms inhabited a world that was profoundly peaceful by later standards. They were all soft-bodied, with no means of harming one another and apparently no need for defense against predators. They lived in communities that resembled underwater gardens, where competition seemed minimal and cooperation was a dominant strategy. Some Ediacaran organisms were flat and leaf-like, designed to maximize their surface area for absorbing nutrients directly from the seawater. Others were tall and frond-like, swaying in the currents like primitive sea ferns. Still others formed colonial structures where many individuals worked together to create elaborate, carpet-like communities. The absence of any shells, teeth, claws, or other hard parts in Ediacaran organisms suggests that this was truly a Garden of Eden period in Earth's history, a time when life had achieved considerable complexity and size without the evolutionary pressure predation that would drive later developments. These remarkable organisms dominated Earth's ocean for nearly 50 million years, creating the first truly complex ecosystems in our planet's history. They established ecological relationships that prefigured many of the interactions we see in modern marine communities, yet they did so in ways that seem almost impossibly gentle and cooperative. But this peaceful world was not destined to last. Deep within the Earth, the same tectonic forces that had assembled Rodinia were beginning to reverse course. The supercontinent was starting to develop internal stresses that would eventually tear it apart and create conditions for the next great chapter in life's story. The breakup of Rodinia, which began approximately 750 million years ago, was as gradual and inexorable as its formation had been. Like a massive ice sheet developing cracks under its own weight, the supercontinent began to split along lines of geological weakness that had been created during its original assembly. The process was not violent in human terms. There were no sudden catastrophic rifts or explosive separations. Instead, Rodinia slowly stretched and thinned along certain zones until new ocean basins began to open between the separating continental fragments. This breakup would take nearly 200 million years to complete, but its effects on Earth's climate and life will be profound and lasting. As new oceans opened between the separating pieces of Rodinia, seawater began to circulate in patterns that had been impossible during the supercontinent's unified existence. Ocean currents that had flowed in simple, continental-scale patterns became more complex and dynamic. The circulation of heat around the planet became more efficient, but also less predictable. Some of the continental fragments that broke away from Rodinia drifted toward Earth's poles, where they began to accumulate ice and snow for the first time in hundreds of millions of years. This was the beginning of a period that geologists call Snowball Earth, an extreme ice age during which glacier may have extended all the way to the equator. The contrast between the warm, stable climate of unified Rodinia and the harsh, variable conditions that followed its breakup was dramatic. Ocean levels dropped as water became locked up in continental ice sheets. The chemistry of seawater changed as new patterns of ocean circulation brought different types of water masses into contact with each other. These environmental changes created strong evolutionary pressures that had not existed during the peaceful Ediacaran period. Organisms that had thrived in stable, subtropical conditions suddenly found themselves in a world of temperature extremes, fluctuating sea levels, and changing ocean chemistry. Many Ediacaran species became extinct during this transition, unable to adapt to the new conditions. But those that survived were forced to develop new strategies for dealing with environmental stress. Some developed the first hard shells and skeletons, providing protection against both physical damage and chemical changes in seawater. Others began experimenting with active predation for the first time in Earth's history. The peaceful, cooperative world of the Ediacaran period was giving way to something more competitive and dynamic. The evolutionary arms race between predators and prey was about to begin in earnest. The fragmentation of Rodinia also created a much more diverse range of marine environments than had existed during the supercontinent's unified period. Shallow tropical seas, deep ocean basins, polar waters, and everything in between provided new ecological niches for organisms to exploit. This environmental diversification set the stage for what paleontologists call the Cambrian explosion, the most dramatic burst of evolutionary innovation in Earth's entire history. Life was about to discover not just complexity, but also beauty, predation, and the endless creativity that comes from evolutionary competition. 541 million years ago, as if someone had suddenly turned on the lights in a darkened room, life on Earth exploded into a symphony of forms that continues to amaze scientists today. The Cambrian explosion represents the moment when evolution discovered art, when natural selection began sculpting creatures of such bizarre beauty and alien magnificence that they seemed like products of science fiction rather than natural history. The oceans that filled the basins between Rodinia's separating fragments became showcase galleries for evolution's newfound creativity. Within a relatively brief period, perhaps 10 to 15 million years, which is mere moments in geological terms, life invented almost every major body plan that exists today, plus many others that have since become extinct. Consider Pangaea, a creature so strange that scientists initially couldn't determine which end was its head. 5 mushroom-shaped eyes dotted its back like organic periscopes, whilst a flexible proboscis ending in a grasping claw extended from its front end. It moved through Cambrian seas like a living submarine, using its bizarre appendage to capture prey in ways that seem almost mechanical by biological standards. Wiwaxia resembled a medieval knight's helmet that had somehow learned to walk. Its back was covered by rows of protective spines and scales that gleamed with iridescent colors, whilst underneath, a soft body moved along the seafood grazing on bacterial mats. Each spine was a masterpiece of biological engineering, hollow and lightweight yet strong enough to deter the most determined predators. Hallucigenia earned its name from its dreamlike appearance, so bizarre that paleontologists initially reconstructed it completely upside down. Rows of defensive spines ran along its back, whilst underneath, 7 pairs of walking legs carried it across the Cambrian sea flue. At one end, a flexible neck ended in a simple head with 2 dark eyes, giving it an almost whimsical expression despite its fearsome armament. But perhaps the most magnificent creature of the Cambrian seas was Anomalocaris, a giant that could reach lengths of 2 meters or more. Picture a creature that moved through the water like an organic spaceship, its body undulating gracefully whilst two enormous appendages at its front end swept through the water like flexible arms. These weren't true arms in any modern sense, but rather flexible feeding structures lined with sharp spines that could grasp and manipulate prey with surprising dexterity. The head of Anomalocaris was dominated by two enormous compound eyes, the largest eyes that had ever existed at that point in Earth's history. Each eye contained thousands of individual lenses, providing vision so acute that this ancient predator could spot potential prey from remarkable distances. Its mouth was a circular structure surrounded by plates that could open and close like the petals of some predatory flower. The development of vision during the Cambrian period represents one of evolution's greatest breakthroughs. For billions of years, life had existed in essential blindness, navigating by chemical cues and physical contact alone. The invention of true image-forming eyes changed everything, creating the first arms race between those who could see and those who needed to hide. Trilobites, perhaps the most successful arthropods ever to evolve, developed compound eyes of stunning sophistication. Some species had eyes containing more than 15,000 individual lenses, providing vision that may have been superior to many modern insects. These eyes were made of calcite, the same mineral that forms limestone, arranged in geometric patterns of mathematical precision. The trilobites themselves were marvels of biological engineering. Their segmented bodies were covered by jointed shells that provided both protection and flexibility. They could roll up into perfect balls when threatened, like biological armadillos, or extend their bodies for efficient swimming and crawling. Some species developed elaborate head shields with sweeping spines, whilst others remained sleek and streamlined for life in the open ocean. In deeper waters, creatures like Pangaea, the lace crab, filtered nutrient from the water column using delicate, feathery appendages. Despite its common name, Pangaea wasn't actually a crab or even closely related to modern crustaceans. It represented an entirely separate evolutionary experiment in arthropod body design, one that proved successful for millions of years before eventually becoming extinct. The Cambrian seas were filled with countless other innovations. Pangaea, one of the earliest known chordates, possessed the first primitive backbone, a flexible rod called a notochord that provided structural support whilst allowing for efficient swimming. This seemingly simple innovation was a foundation upon which all vertebrate life, including humans, would eventually be built. Shell building reached new heights of sophistication during this period. Brachiopods developed intricate internal structures for filtering food from seawater, whilst early mollusks experimented with shells of every conceivable shape and ornamentation. Some shells were smooth and streamlined, others were covered with elaborate spines and ridges that may have served both defensive and display functions. The Cambrian explosion wasn't limited to animals. Algae evolved into forms of unprecedented complexity and beauty, creating underwater forests that provided habitat and food for countless other organisms. Some algae developed calcified skeletons, contributing to the first major reef systems in Earth's history. But even as this biological renaissance was reaching its peak, the continents themselves are preparing for another dramatic reorganization. The fragments of Rodinia continued their slow drift across Earth's surface, and new patterns of continental assembly were beginning to emerge. Whilst the Cambrian explosion was transforming life in the oceans, the continental fragments that had once formed Rodinia were beginning to drift back together, pulled by the same deep mantle currents that had originally torn the supercontinent apart. This reassembly process would create Earth's next supercontinent, though it would be smaller and more short-lived than mighty Rodinia. Approximately 600 million years ago, many of these continental fragments began converging to form Pangaea, whose name means all southern in reference to its primarily southern hemisphere location. Unlike Rodinia, which had been a massive, long-lived supercontinent, Pangaea was a more modest assembly that existed for only about 60 million years before beginning to fragment again. Pangaea's structure was quite different from its predecessor. Rather than forming one enormous landmass, the converging continents created a configuration more like a broken chain of large islands and peninsulas. This gave Pangaea a much more complex coastline than Rodinia had possessed, with numerous bays, inlets, and shallow seas separating different parts of the supercontinent. The climate during Pangaea's existence was generally milder and more stable than the Ice Age conditions that had characterized Rodinia's breakup. The supercontinent's fragmented structure allowed ocean currents to circulate more freely, moderating temperature extremes and creating a more hospitable environment for continued evolution of complex life. The shallow seas that surrounded and penetrated Pangaea's coastlines became nurseries for some of the most important evolutionary developments in Earth's history. These warm, protected waters provided ideal conditions for continued diversification that had begun during the Cambrian explosion. It was during Pangaea's existence that many of the major animal phyla established the basic body plans that their descendants still follow today. Arthropods refined their segmented body architecture and jointed limbs. Early chordates developed more sophisticated nervous systems and sensory organs. Mollusks experimented with increasingly elaborate shell designs and soft body modifications. The reefs that grew in Pangaea's shallow seas were unlike anything that exists today. They were built primarily by extinct organisms called archaeocyathids, sponge-like creatures that constructed elaborate, cup-shaped skeletons from calcium carbonate. These ancient reef builders created some of the most complex ecosystems yet seen on Earth, supporting hundreds of different species in intricate webs of interdependence. But Pangaea's fragmented structure also made it inherently unstable. The same geological forces that had brought its constituent continents together began pulling them apart almost as soon as the supercontinent had fully formed. Unlike Rodinia's long period of unified existence, Pangaea began showing signs of internal stress and separation within a few million years of its completion. The breakup of Pangaea was more complex and chaotic than Rodinia's relatively simple fragmentation. Instead of splitting into a few large pieces, Pangaea dissolved into numerous smaller continental fragments that scattered across the globe like leaves blown by an autumn wind. This created a world of unprecedented geographical complexity, with continents and large islands distributed across all latitudes and climatic zones. After Pangaea's dissolution, approximately 540 one of the most geographically diverse periods in its entire history. Instead of being dominated by one or two massive supercontinents, the planet became a world of medium-sized continents, large islands, and extensive archipelagos, all separated by broad oceans and connected by complex current systems. This fragmented continental configuration created an extraordinary range of marine environments. Tropical seas developed between continents positioned near the equator, whilst colder waters surrounded landmasses that had drifted toward the poles. Shallow epicontinental seas, bodies of water that covered portions of the continental shelves, created vast areas of warm, nutrient-rich habitat ideal for marine life. The geographic isolation created by this continental fragmentation had profound evolutionary consequences. Populations of organisms that had once been connected by shallow seas or land bridges found themselves separated by deep ocean basins. This isolation allowed different populations to evolve independently, creating the first truly global diversification of life forms. Some continents developed their own unique assemblages of organisms, early versions of the biogeographic provinces we see today. Islands and isolated continental shelves became natural laboratories for evolutionary experimentation, where life could develop in directions that would have been impossible in more connected environments. The complex ocean circulation patterns created by this fragmented geography also had important climatic effects. Deep ocean currents could flow more freely between ocean basins, creating more efficient global circulation of heat and nutrients. This helped moderate climate extremes and created more stable conditions for continued biological evolution. It was during this period of continental fragmentation that life began its most ambitious expansion yet, the colonization of dry land itself. For nearly 4 billion years, life had been exclusively aquatic, confined to oceans, lakes, and rivers. But the extensive coastlines and varied terrestrial environments created by the scattered continents provided new opportunity for organisms willing to venture beyond the safety of aquatic environments. The first terrestrial pioneers were not animals, but rather simple plants and fungi that could survive in the harsh conditions of the boundary between land and sea. These early colonists faced challenges that no life form had ever encountered before: dramatic temperature fluctuations, intense solar radiation unfiltered by water, and the constant threat of desiccation. The transition from water to land required fundamental changes in virtually every aspect of an organism's biology. Respiratory systems had to be redesigned to extract oxygen from air rather than water. Structural support systems needed to function without the buoyancy provided by aquatic environments. Reproductive strategies had to account for the absence of water to carry sperm and eggs. Despite these challenges, some organisms proved remarkably adaptable to terrestrial conditions. Simple plants like mosses and liverworts developed waxy coatings to prevent water loss and specialized structures for absorbing moisture from the air. Primitive fungi established partnerships with these early plants, helping them extract nutrients from rocky soils in exchange for organic compound produced through photosynthesis. 470 million years ago, these pioneering organisms began creating Earth's first terrestrial ecosystems. They were modest affairs by latest standards, thin mat of moss and lichen covering rocky surfaces near coastlines and riverbanks. But they represented the beginning of one of life's greatest adventures, the conquest of the continents. Following these plant pioneers came the first terrestrial animals, arthropods that had modified their aquatic ancestors' body plan for life on dry land. Early millipedes and primitive arachnids found rich feeding opportunities in the organic matter accumulating around the first plant communities. These early terrestrial arthropods faced many of the same challenges as plants, avoiding dehydration, dealing with temperature extremes, and navigating in three-dimensional terrestrial environments. The sound environment of these early terrestrial ecosystems were profoundly different from anything we might experience today. There were no bird songs, no insect choruses, no rustling of leaves in complex forest canopies. Instead, the early terrestrial world was characterized by the gentle sounds of wind moving through simple plant communities and the occasional scuttling of arthropods across rock surfaces. But even these modest beginnings were preparing the way for one of the most dramatic transformations in Earth's history. As plants and animals continued to adapt to terrestrial environments, they would eventually create the complex forest ecosystems that would define the later Paleozoic era. During the Devonian period, approximately 400 million years ago, Earth experienced what paleobotanists call the Devonian explosion, a rapid diversification of terrestrial plant life that created the first true forests. This transformation was as dramatic in its own way as the earlier Cambrian explosion in marine environments, but it played out on land rather than in the sea. The key innovation that made Devonian forests possible was the evolution of vascular tissues, specialized structures that could transport water and nutrients throughout a plant's body. This seemingly simple development allowed plants to grow much larger than their non-vascular predecessors and to colonize environments far from reliable water sources. Archaeopteris, one of the most successful early trees, could reach heights of 30 meters, creating the first forest canopies in Earth's history. But unlike modern trees with their broad leaves, Archaeopteris bore delicate, fern-like fronds that gave these ancient forests an otherworldly appearance. Imagine walking through woodland where every tree resembled a giant fern, with canopies that filtered sunlight into dappled patterns unlike anything in our modern world. Other early trees followed different evolutionary strategies. Lepidodendron, the scale tree, developed a trunk covered in diamond-shaped leaf scars that gave it a distinctive geometric appearance. Some specimens reached heights of 40 meters, making them among the tallest organisms that had ever existed on land. Despite their impressive size, these early trees were more closely related to modern club mosses than to any contemporary tree species. The understory of Devonian forests was dominated by giant ferns and early seed plants that experimented with numerous reproductive strategies. Some developed elaborate spore-bearing structures, whilst others began experimenting with seeds, protective packages that could survive harsh conditions and germinate when favorable environments returned. These forests created Earth's first complex terrestrial ecosystems, with multiple layers of vegetation providing habitat for an increasingly diverse array of animal life. The forest floor accumulated the first substantial deposits of organic matter on land, creating soils far richer than anything that had existed during the early colonization period. In streams and ponds within these forests lived the first terrestrial vertebrates, amphibians that had evolved from lobe-finned fish during the late Devonian period. Early amphibians like Acanthostiga retained many fish-like characteristics, including gills and fins, but they had also developed primitive lungs and limb-like appendages that allowed them to venture onto land for short periods. The aquatic environments within Devonian forests were dominated by armored fish that had reached unprecedented sizes. Dunkleosteus, the largest predatory fish of its time, could reach lengths of 10 meters and possess jaw muscles capable of generating bite forces comparable to those of Tyrannosaurus rex. These ancient waters were far more dangerous than modern freshwater environments, filled with predators that could easily destroy any modern fish foolish enough to venture into their domain. The atmospheric composition during the Devonian period was quite different from today's. Oxygen levels were significantly higher, reaching concentrations of 35% compared to our current 21%. This oxygen-rich atmosphere supported the metabolism of large terrestrial arthropods that could never survive under current conditions. Giant dragonflies with wingspans approaching 1 meter patrolled the airspace above Devonian forests, whilst millipedes longer than modern snakes crawled across the forest floor. The high oxygen content also supported more efficient plant metabolism, contributing to the rapid growth and large size of early forest trees. But even as these terrestrial ecosystems were reaching new levels of complexity, the continental fragments that had been scattered since Penosia's breakup were beginning to move toward each other once again. The patient forces of plate tectonics were preparing to assemble Earth's next supercontinent, a massive landmass that would eventually become more famous than any of its predecessors. The convergence that would create this new supercontinent began with a gradual approach of two major continental assemblages. In the northern hemisphere, smaller continents and island chains were coalescing into a large landmass that geologists call Laurasia. Meanwhile, in the southern hemisphere, an even larger collection of continents was forming Gondwana, a massive southern supercontinent that would persist for hundreds of millions of years. Laurasia included what would eventually become North America. The collision and suturing of these continental fragments created mountain ranges that rivaled any in Earth's history. The Appalachian Mountains of eastern North America, the Caledonian Mountains of Scotland and Scandinavia, and the Ural Mountains of Russia all formed during this period of continental assembly. Gondwana was even more impressive, incorporating what would eventually become South America, Africa, Antarctica, Australia, India, and numerous smaller landmasses. This southern supercontinent was so large that it extended from polar regions to well into the northern hemisphere, encompassing nearly every climatic zone on Earth. Between Laurasia and Gondwana lay the Tessus Ocean, a body of water that would play a crucial role in global climate and ocean circulation for hundreds of millions of years. The Tessus was a tropical sea, warm and shallow, that supported some of the most diverse marine ecosystems in Earth's history. The climate during this period of dual supercontinents was remarkably stable and warm. There were no polar ice caps, and tropical conditions extended much further toward the poles than they do today. Vast coal swamps covered large portions of both Laurasia and Gondwana, accumulating organic matter that would eventually become the coal deposits that powered the Industrial Revolution. These carboniferous swamps were unlike any modern ecosystem. Giant club moss trees formed dense, humid forests where the understory was dominated by tree ferns and early seed plants. The combination of high atmospheric oxygen and warm, humid conditions created environments that supported arthropods of unprecedented size. Griffin flies, ancient relatives of dragonflies, reached wingspans of 70 centimeters, making them the largest flying insects ever to exist. Giant millipedes called Arthroplura could reach lengths of 2 meters, whilst primitive arachnids experimented with body plans that have no modern equivalents. In the waters of the coal swamps lived amphibians that had grown to impressive sizes. Labyrinthodonts, named for the complex folding of their tooth enamel, included species that reached the size of modern crocodiles. These were the dominant predators of freshwater environments, filling ecological niches that would later be occupied by reptiles and mammals. The plant communities of carboniferous swamps were incredibly productive, accumulating organic matter faster than it could decompose in the warm, oxygen-poor waters. Over millions of years, this organic accumulation created vast peat deposits that would eventually be compressed and transformed into coal, the fossilized remains of these ancient forests. But the age of dual supercontinents was drawing to a close. Laurasia and Gondwana continued their slow but inevitable approach toward each other, carried by the same deep mantle currents that had assembled and dispersed previous supercontinents. The Tessus Ocean between them gradually narrowed as the two landmasses converged. The collision between Laurasia and Gondwana was not a sudden event, but rather a prolonged process of continental suturing that lasted tens of millions of years. As the leading edges of the two supercontinents made contact, they began to buckle and fold, creating mountain ranges of unprecedented scale and grandeur. The Appalachian Mountains, which had been formed during Laurasia's initial assembly, were uplifted and extended as a collision progressed. Similar mountain building occurred along the suture zone between the converging supercontinents, creating highland regions that stretched for thousands of kilometers. Finally, approximately 300 million years ago, the long process of continental convergence reached its culmination. Laurasia and Gondwana had become fully welded together along their collision zone, creating the largest supercontinent in Earth's history, Pangaea, whose name means all land in ancient Greek. The formation of Pangaea marked the end of an era in Earth's geological history. For hundreds of millions of years, the planet had been characterized by multiple continents, complex ocean circulation patterns, and diverse climatic zones. Now, for the first time since Rodinia's ancient reign, nearly all of Earth's dry land was united in a single massive continent. Pangaea was shaped like an enormous sea, with a deep embayment on its eastern side where the ancient Tessus Ocean persisted as a large Mediterranean Sea. The supercontinent extended from pole to pole, encompassing nearly every climatic zone on Earth within its vast borders. Its western shores faced Pangaea, the All Sea, an ocean so vast that it covered more than half of Earth's entire surface. The assembly of Pangaea had profound effects on global climate and ocean circulation. The reduction from multiple continents to a single landmass simplified atmospheric and oceanic circulation patterns dramatically. Weather systems could now develop on truly continental scales, creating climatic patterns unlike anything that exists in our modern world of separated continents. The interior of Pangaea was dominated by vast deserts that stretched for thousands of kilometers without interruption. These were among the most extensive arid regions in Earth's history, created by the simple fact that moist air masses from the ocean could not penetrate effectively into the supercontinent's central regions. Seasonal temperature variations in Pangaea's interior were extreme. Without nearby oceans to moderate climate, central regions experienced scorching summers and frigid winters, with temperature swings that far exceeded anything found in our current world. Monsoon systems of unprecedented intensity developed, bringing torrential rains during wet seasons followed by prolonged droughts. Despite these harsh conditions, life found ways to adapt and even thrive in Pangaea's challenging environments. Plants developed increasingly sophisticated mechanisms for conserving water and surviving extreme temperature fluctuations. Early conifers spread across vast regions of the supercontinent, creating the first truly continental-scale forests. Animal life during Pangaea's early history was dominated by amphibians and early reptiles that had evolved improved methods for surviving on dry land. The development of the amniotic egg, a self-contained reproductive package with its own water supply, freed reptiles from dependence on aquatic environments for reproduction. Early reptiles diversified rapidly in Pangaea's varied environments. Some remained small and retained many primitive characteristics, whilst others grew to impressive sizes and developed specialized feeding strategies. The first herbivorous reptiles appeared, followed by increasingly sophisticated predators that filled niches previously occupied by large amphibians. But Pangaea's existence will be marked by one of the most severe crises in life's history. At the end of the Permian period, approximately 250 million years ago, Earth experienced its greatest mass extinction event. This catastrophe, sometimes called the Great Dying, eliminated more than 90% of marine species and 70% of terrestrial vertebrates. The causes of the end Permian extinction remain debated, but most scientists believe it resulted from massive volcanic eruptions in what is now Siberia. These eruptions released enormous quantities of carbon dioxide and toxic gases into the atmosphere, creating a greenhouse effect that raised global temperatures to levels incompatible with most existing life forms. The extinction created vast ecological vacuums that were gradually filled by new forms of life better adapted to Pangaea's extreme conditions. Early dinosaurs appeared during the Triassic period, along with the first mammals, marine reptiles, and many other groups that would dominate later periods. Flying reptiles called pterosaurs took to the skies, becoming the first large vertebrates to achieve powered flight. Marine reptiles like ichthyosaurs and plesiosaurs colonized Pangaea's surrounding oceans, reaching sizes and developing specializations that rivaled those of modern whales. Plant communities also underwent major changes during this period. The first flowering plants appeared, though they would not become dominant until much later in Earth's history. Cycads and other primitive seed plants created park-like landscapes in many regions, whilst conifers formed extensive forests in cooler and higher elevation areas. Throughout Pangaea's existence, the supercontinent continued to be affected by the same geological processes that had created it. Deep within Earth's mantle, convection currents that had brought the continent together began to change direction, creating new patterns of heat flow that would eventually tear Pangaea apart. The first signs of Pangaea's eventual breakup appeared relatively early in the supercontinent history. Rift valleys began forming in various regions, particularly along lines of geological weakness created during Pangaea's original assembly. These early rifts were precursors to the ocean basins that would eventually separate the modern continents. Volcanic activity increased along these developing rift zones, creating long chains of volcanoes and associated lava flows. The most extensive of these volcanic provinces formed along what would eventually become the Atlantic Ocean, where massive eruptions marked the beginning of Pangaea's dissolution. 175 million years ago, the forces that had been building within Pangaea for tens of millions of years finally overcame the structural integrity that held the supercontinent together. The Great Breakup began with the opening of the Central Atlantic Ocean, a narrow seaway that gradually widened as North America separated from Africa. This initial separation was followed by a complex sequence of continental rifting and ocean basin opening that would eventually create the familiar pattern of continents and oceans we know today. South America began separating from Africa, creating the South Atlantic. India started its epic journey northward toward Asia. Antarctica and Australia began their long drift toward the South Pole. Each new separation created opportunities for evolutionary innovation and adaptation. Populations of organisms that had been connected across Pangaea's united landscape found themselves isolated on different continents, free to evolve independently in response to local environmental conditions. The breakup of Pangaea also had profound effects on global climate and ocean circulation. As new ocean basins opened, seawater could circulate in more complex patterns, creating more efficient heat distribution around the globe. The formation of the Atlantic Ocean allowed the development of current systems that persist to this day. Continental positions continued to evolve throughout the Mesozoic era, gradually approaching configuration we know today. India's collision with Asia created the Himalayas, the world's highest mountain range. The opening of the Drake Passage between South America and Antarctica allowed the development of the Antarctic Circumpolar Current, which isolated Antarctica and contributed to the formation of its ice sheets. By the beginning of the Cenozoic era, 6 to 5 million years ago, the continents had achieved positions roughly similar to those they occupy today, though they have continued to move and will continue moving for billions of years to come. The age of Pangaea was over, replaced by the more familiar world of separate continents and interconnected but distinct ocean basins. Today, as we stand on our modern continents and gaze across our contemporary oceans, we are witnessing merely the latest chapter in an ongoing story of continental drift and geological change. The forces that assembled and dispersed Rodinia, Pangaea, and Pangaea continue to operate, slowly but inexorably moving the continent toward future configurations that we can only imagine. In this vast sweep of geological time, we have seen our planet transform from a world of scattered volcanic islands to one dominated by supercontinents, then fragment again into the familiar configuration of our modern Earth. We have witnessed the emergence of life from chemical soup, its evolution from simple cells to complex organisms, and its expansion from ocean depths to continental heights. The story of Earth before Pangaea is ultimately a story about time itself, deep time that operates on scales so vast that human lifespans seem like mere moments in comparison. It is a story about change and continuity, about the patient processes that have shaped our world across billions of years and continue to shape it today. Each mountain range tells a story of continental collisions that occurred hundreds of millions of years ago. Every ocean basin carries memories of the supercontinents that once separated its shores. The very air we breathe was transformed by the photosynthetic organisms that lived when our planet was young and continents were still learning their eternal dance. We are all children of this deep history, carrying within our bodies the elements forged in ancient stars and organized by billions of years of geological and biological evolution. Our DNA preserves the molecular memory of organisms that lived in Archean seas, whilst our bones are built from calcium that may have been part of Cambrian shells or Devonian reefs. In contemplating these vast timescales and enormous changes, we gain perspective on our own place in the continuing story of our planet. We live in a dynamic world where continents still drift, mountains still rise, and life still evolve in response to ever-changing conditions. The processes that created the supercontinents of the past continue to operate today, slowly but inevitably working toward future geological arrangements that our descendants may witness. Perhaps in some distant future, hundreds of millions of years hence, Earth's continents will once again assemble into a new supercontinent, creating conditions as different from our current world as Pangaea was from the scattered continents that preceded it. Life will adapt to these new conditions just as it has adapted to every previous change in Earth's long history. The deep time perspective reminds us that change is the only constant in Earth's history, and wonder
What seems
at the
permanent
incredible
and
unchanging in our processes that have created the actually part of a dynamic system. In closing our journey through these ancient years, and will continue to return to the present with a deep appreciation. This knowledge brings humility and wonder, written in the rock, humility at our small place around our story. Every creature we encounter, every landscape we traverse, every breath of air we take connects us to this incredible 4 billion year story of planetary evolution. The Earth before Pangaea was a world of infinite possibility, where every geological process and biological innovation contributed to the rich tapestry of existence we experience today. Understanding this history enriches our appreciation of the present and helps us recognize our responsibility as temporary custodians of this remarkable planetary heritage. May this contemplation of deep time bring peace and perspective, reminding us that we are participants in a story much larger and more wonderful than any individual mind can fully comprehend. The history of our Earth belongs to all humanity, and perhaps to any intelligence that might one day succeed us, carrying forward a long tradition of consciousness marveling at the universe that created it.